Hi students, in this lecture we are going to discuss a few problems. See the first one. An ideal gas is enclosed in cylindrical vessel with a piston of mass m and cross-section area A. Pressure of the gas is P and length of the gas column is L. Find the period of small oscillations of the piston if the piston is slightly pushed down. Assume temperature of the gas constant. So here let us make a diagram for this question. There is a piston, cylinder, and a piston is there, and it is given mass of piston is m. If it is slightly pushed down, slightly pushed inside, so first we have to focus who is providing a restoring force. Okay, so here you can see when we are pushing the piston inside, volume is decreasing. So when volume decreasing, pressure of the gas increases. So taking gas equation PV equal to nRT, number of moles constant, no change in temperature. So volume is decreased, so pressure of the gas increases. So this increase in pressure provides extra force on the piston. So I'm showing a diagram. Here you can see by the gas on the piston having now extra force because of extra pressure, and that extra force providing now a restoring force. And to calculate that extra pressure, so take here gas equation. Now condition for constant temperature, PV equal to constant, and differentiate that. So PdV plus VdP equal to 0, differentiating PV equal to constant. Now from that getting extra pressure, or you can say change in pressure, that is equal to minus P dV by V. Then see from that what we get. So we got extra pressure. So restoring force F equal to dP extra pressure into area. Extra pressure is now minus P into dV. In the place of dV, I can write area into displacement is X inside. That is a dV by volume. Volume is now area into, it is given length of the gas column is L. So A into L gives volume of the gas into area. So this is now restoring force. So from here, area gets cancelled. Remaining is now, it is PA by L into X. Of course, taking here negative sign, which indicates displacement is inwards, but force is outwards. So it is of the form minus K into X. That means here force constant is PA by L. So now taking here time period is 2 pi root m by K. So in the place of K, PA by L. So time period of a small oscillations is 2 pi root m L by PA. So like this, we have to focus what is the restoring force. Okay, right. Let us see next problem. A particle is confined to move along x-axis, and the net force acting on the particle as a function of position is given as F equal to minus 15x plus 3. Find time period of oscillations. Right. See, force is given as a function of position coordinate. Again, here we have to focus what is now restoring force. So here you can see this force becomes 0 when x equal to 1 by 5. That means x equal to 1 by 5 is mean position, right? That means for that x value, f is 0. So if you have a small displacement from mean position, then we have to focus what is the net force acting on that. And that becomes restoring force. So here I have taken derivative of that, differentiate. So df equal to minus 15 dx. So here dx stands for displacement and df is restoring force. That means in the place of k, it is now 15. So force constant is 15. Then time period is 2 pi root m by k. Otherwise, the same thing you can solve it as, I will write here, f equal to minus 15. I am taking it outside. Remaining is x minus 1 by 5. Means without differentiating that. So here x corresponds to position coordinate. X minus 1 by 5 corresponds to displacement. Displacement from mean position. So this is of the form minus 15 into displacement. So either you can solve like this or you can solve by differentiating that. Okay. Right. See next one. Right. Read the question. A ball is hung vertically by a massless, inextensible string of length L from a point P of an inclined wall that makes an angle beta with the vertical. The thread with the ball is then deviated through a small angle alpha, alpha greater than beta, and released. Assume the collision between the wall and the ball is elastic. Find the period of oscillations of that pendulum. So you can see here when pendulum is oscillating, angle made by that pendulum with vertical is changing. So this is an example for angular simple harmonic motion, right? So I have taken here. So theta equal to theta naught cos omega t, where theta naught stands for maximum angular displacement. So in this problem, alpha is now maximum angular displacement. And let us consider here, let us consider anti-clockwise as opposed. This is a complete our choice. Therefore, alpha is positive because when we measure from the vertical, it is anti-clockwise. So alpha positive and beta is negative. So alpha positive, beta negative. So I have written here beta negative and alpha positive. And you have to see why we have taken cos function. In the question, it is given that ball is then deviated through a small angle alpha, then released. So released means their angular velocity equal to 0. So angular velocity is 0 at extreme positions. That's why we have taken it is cos omega t. Now see what's the value of t. So t equal to 1 by omega cos inverse minus beta by alpha. So this is a time taken by the pendulum to make a collision with the wall. I am repeating. So here we have taken directly minus beta equal to alpha into cos omega t. So this time is giving us the time taken by the pendulum to make a collision with the wall. And in the question it is given, find the period of oscillations of that pendulum. So here one time period means making the collision with the wall and coming back to right extreme. Coming back to right extreme. This is one oscillation. Therefore, time period is t equal to 2 small t. So I have taken the place of omega root of g by l. Therefore, answer is 2 into root of l by g. And cos inverse minus beta by alpha is taken as pi minus cos inverse beta by alpha. And this can also be written as, so you are knowing that sin inverse x plus cos inverse x equal to 90. So in the place of minus cos inverse beta by alpha, in the place of cos inverse beta by alpha, see what we can write there? That is equal to 2 root of L by G pi minus, in the place of that cos inverse, we are writing it is a pi by 2 plus sine inverse beta by alpha, right? Then answer comes out to be 2 root of L by G into pi by 2 plus sine inverse beta by alpha. Either we can write in this way or we can write in this way in terms of cos inverse beta by alpha. Okay. Let us see now next problem. Read the question carefully. A particle of mass m is suspended with the help of two massless inextensible strings as shown. Now the particle is given a small displacement perpendicular to the plane of the triangle. Then find period of small oscillations. If you observe carefully in diagram, distance of this point mass from the ceiling, that is a constant. It is given oscillations perpendicular to plane of the triangle. So during this, distance of this mass from ceiling is a constant. That means this is an example for simple pendulum. And we have to calculate now its length how much. Okay. We have to calculate now its length is how much. So take it as now x. Its length is now x. Then see what we can do. So I'm making a diagram once again. This is x and see total value given 7L. Let us take this value. This is y. Remaining is now 7L. Wait, here what we have taken x. So first we have taken x square plus y square. Okay. Here we have taken, this is y. This is not x. According to the calculation part given here, this is x. So that is y, and this is x. So x square plus y square is equal to 3 root 2 whole square. That is now 18. Okay. And coming to here, this remaining part is 7l minus x. Then 7l minus x whole square plus y square is equal to 5 square l, that is 25. This is a 5l. This is 3 root 2l. So solving now equation 1 and equation 2, solving these two, we are going to get the value of x, right? After having the value of x, I think in the diagram also we have taken wrong. That is, just cross check once. We have taken the equation x square plus y square equal to 18l square, right? Okay. And 7l minus x. That means here we require the value of y, not x. Okay. So I have to correct here, make correction here. So we got x value, 3l, and once we have x value, from that we can calculate y value. Okay. And once we get y value, time period is 2 pi root L by G. It is now y by G. Okay. So I have taken reverse here, x and y. Just cross check once. This is x. So remaining part is 7l minus x. That is what we have taken in equation 2. Equation 1, x square plus y square equal to 18l square. Okay. So here you have to calculate y value. Then time period is 2 pi root y by g. So this is not correct. 3l. So make change here. Okay. In the place of 3l, get the value of y. Right. Okay. Let us go for next problem. Right. Read the question. A particle is placed at the lowest point of a smooth parabolic surface whose equation is given as x square equal to 5y, where x and y are in meter. If it is slightly disturbed from its mean position, then it executes a Shm. Find period of its small oscillations. So read the question carefully, try of your own. After trying, you can follow the solution part. Let us make a diagram for this given data. It is given parabolic shape, x square equal to 5y. That means y value positive, whether x is positive or negative. That means I have to make a diagram like this, right? So taking this as y-axis and this as x-axis. If it is slightly disturbed from its mean position, let us take, now this is location of the particle. Okay. Then see what happens. Angle made by the position vector with the vertical. So take it as a theta. Now see how many forces acting on the particle. One is mg. Second one is normal reaction. Only two forces acting on the particle. Now we have to focus who is providing a restoring force. So it is very clear that one component of mg is providing a restoring force, that is mg sin theta. So here we have taken restoring force equal to minus mg sine theta, right? That is equal to mg tan theta. So here you should be very careful. Why we have replaced sine theta with tan theta? Whenever theta very small, we can write sine approximately equal to tan. So I am writing that logic once again. So tan theta is equal to sine theta by cos theta. Since theta is very small, cos theta approximately equal to 1. When cos value is 1, tan equal to sine. That's why here we have written in the place of a sine tan theta. Next, we have to find what is the value of tan theta. From the diagram, tan theta gives a slope. So you see equation now, x square equal to 5 into y. From that, 2x dx is equal to 5 into dy. So from here, slope equal to dy by dx, which is equal to 2x by 5. That is what we have written here, right? So now restoring force is minus 2mgx by 5, right? So what is now here force constant? 2 mg by 5, right? Therefore, time period is 2 pi root m by k. Then we get the final answer, right? So here the main thing is getting restoring force. And to get that, we have taken sine approximately equal to tan. So getting this idea is very important, right?